I think there's 34 slides, so it's another 10 slides. So your NAS and elimination addition reactions, can't see them as being super likely on showing up. I don't think I actually put a whole lot on this slide. Yeah, until I put a lot of effort into that one. These, for them to work, they have to be electron deficient aromatic rings. So you're looking at electron withdrawing groups. Your classic case, what was that? Yep. You're looking at your nitro attached to the ring.
And there was one question with Tilda. So that's an even better situation.
That would be an even better situation. In both your NAS and your elimination addition, not only does it need to be electron withdrawing, but you need a leaving group. So if it's just nitrobenzene, that's a pretty useless structure. You have to have that leaving group on there as well. And then where it's located, it is probably dependent on the electron withdrawing group. So if we pull electron density out, yep, there it goes. What charge builds on this carbon? A positive charge. If we did resonance, what charge builds on that carbon? Positive. Because of the electron withdrawing group, that carbon becomes even more positive, more electrophilic, which is exactly what we want for the NAS reaction, because we want our nucleophile to be able to come in and kick that guy out. Okay. So we do need that good leaving group. Your nucleophiles, you're often looking at OH or NH2. Okay, those are pretty much the only ones that you'll see. The elimination addition means you go through the benzyne intermediate. Okay. I would be kind of surprised if that showed up on the ACS test, your benzyne intermediate. It's possible, but just kind of surprised. The reason why it would be possible is it's just weird to have a triple bond in a ring. Okay, so they might look at it and say, hey, that's kind of cool. Let's ask a question about it. The reason why the benzyne becomes more important is that means your nucleophile can come in from either side. So we end up with different products. Okay? Whereas with your NAS mechanism, it only goes where the electrophile is, or where the electrophilic carbon was, where the leaving group left from. Okay. Your carbonyl chemistry, I think we are starting to get to the point where there's not a lot for me to add. I think I actually did a pretty good job summarizing chapter 20 on this one. Everything's pretty much in there. The names are even in there, and I don't think they had any real big typos with this one either. So this, I think, just... Are you kidding me?
The one on the 4 bonds on the nitrogen here at the bottom, right before that double bond.
So you're saying...
The IV has extra hydrogen or an extra argon bond, yeah.
What extra argon?
I don't know what you're talking about. I was smoking crack.
It's just got a giant red blob instead. So yeah, everything else I think is pretty well determined. I would also be surprised on the Behr-Villiger, but I did notice that a lot of people missed that question on the last test. Deciding on how you do that rearrangement is dependent on that list that you had to have memorized. What's that?
They called it a migrating group.
The migrating group, which I guess makes sense because it's not the same as a rearrangement, even though it is effectively a rearrangement. I believe, though I'm not positive, that it goes hydrogen rearranges before your tertiary, before your phenyl, which was roughly the same thing as your secondary, which was better than your primary, better than your methyl. Okay, so if you see a Behr-Villiger show up, that's what's happening with that one. Okay. Anything else interesting in that? don't think so. I don't see anything that particularly jumps out at me as all that interesting.
That's a good slide.
So, chapter 22 was looking at your alpha carbon, and almost to a certain extent the beta carbon as well. But most of that was your alpha carbon. Chapter 20 was that previous slide, looking at all those individual reactions. So in 22, we removed that acidic hydrogen, and now we have a nucleophile, so it can react a billion ways north of, south of the equator. Really, it's 3 o'clock. I've been doing this now for 3 hours. I'm tired. So we really get a nucleophile out of our carbon, or our alpha carbon, which then set up all sorts of other reactions. A lot of these were named. I know this one gets really busy with it. What I tried to do was keep outside of the boxes the actual reaction, and then within the boxes are kind of special cases of that reaction. So the big point out of this chapter is, again, that you can remove that hydrogen, you generate the enolate. The enolate then can then go wicked crazy on you and do all sorts of other fun stuff. Okay. Where I saw a lot of people having issues was with carbons. So if you think you're doing some carbonyl chemistry, count all of the carbons, make sure you haven't lost any. Most of these reactions, you do not lose carbons. Okay? The one exception would be, where have you lost carbons? The CO2 one, the decarboxylation. You do lose a carbon in that case. All other cases, you maintain carbons throughout the reaction. What's that?
Was it the malonic ester?
The decarboxylation comes through your malonic ester, yes. Technically the malonic ester, and then the acetoacetate,
Which is the same thing.
which is effectively the same thing, except one of them is a carbonyl instead of an ester. Okay. We kind of skipped over this section. I also don't expect a whole lot on it, but what we're really looking at is the beta position chemistry now. That beta position is also an electrophile. So if we have an alpha-beta unsaturated ketone, or for that matter aldehyde, that beta position is also an electrophile due to resonance within the structure, which means we can now possibly increase the amount of reactions occurring. With our carbonyls, that carbonyl carbon is still the most electrophilic carbon there, so that if we put in a strong nucleophile, that's where it's going to attack. So when we look at our Grignard reagents, they attack the carbonyl carbon. If we can stabilize the nucleophile a little bit through resonance, we weaken its reactivity to the point where sterics becomes a larger issue and that beta position becomes a little bit more accessible, okay? A little bit more reactive. So, or not more reactive, but more productive, perhaps, would be the way to look at it. So if we have resonance stabilized nucleophiles, we see the beta position reacting and we get the 1,4 conjugate addition, which has to come, or comes from where our species were added. Okay? And the drawing that I've got there, it doesn't work very well, but we've got a 1,4 around our Grignard reagent. In the case of our beta addition, we really had a 1,4. The hydrogen went on first because in our intermediate we had the enol. Once we formed our 1,4 product, it tautomerized and gave us our final carbonyl. Okay, but it's still officially a 1,4 product because we had to form that first. Okay, so if we have that resonance stabilized nucleophile, or if it's stabilized in other ways, in the case they're showing here with the copper, then we'll get that 1,4 addition product. These show up as Gilman reagents, Michael reagents. The Stork-enamine reaction takes advantage of the same general idea, and then you can also see it with the Robinson annulation. Okay? If you're nervous about any of those chemistries, I'd recommend you look it up. I don't think it's going to be that big of a deal or worth the effort to really push for it, I'd stick with kind of the basics right now. Go back to your substitution, eliminations, and your addition reactions, and make sure you know those backwards and forwards, because if you got those squared, you can now spend a little bit more time on the test to try and figure out harder questions like this. Okay. Carboxylic acids, again, I'm not a fan of this slide, but it does show all the individual reactions and what can happen. Remember that your acyl chloride is the highest in reactivity, and then it kind of progresses downwards or from left to right as far as our reactivity goes. Okay. Yeah.
How did we get from the, you drew it the other day from like the, not seeing it on there. The amide back to the chloride one.
So to go from amide
Yeah, that one. There was like
to
two steps.
chloride.
That's something with water?
Yes. To go that direction, what we're doing is we add water
Oh, it really does work that way.
to make the carboxylic acid, and then we can add our thionyl chloride
Oh, okay.
to get there.
That's not where I was looking. Okay, done. It's
Yeah.
right there. Gotcha.
That's one of the reasons why I would argue this is a confusing slide. Okay, there is a lot of stuff jammed on there that really I don't think needs to be. Then what do we have? Yay, amines and bases. That means I'm almost done. So we've really got these three syntheses, as we talked about, I think it was even last week. I really think that you need to check up on your imine chemistry, which is really what's happening out there, the reductive amination. We first go through and form an imine with a carbonyl, and then we reduce it with our H2 and platinum, to get to the final amine product. Okay, that one I would bet is going to show up on the ACS test. Azide might show up, but I doubt I'd see it as a reagent. Where I would expect to see that is for resonance. There's lots of charge within that thing, which is typically something students have trouble with. So they might ask for the azide ion, which of the following is a valid resonance structure. Okay, and they could throw 3 or 4, or which of the following is an invalid resonance structure. Okay, and give you 3 very quick and easy good ones, and then 1 pretty bad one. Okay, so watch out for that one. I would be surprised if it showed up as a synthesis, but I would argue that that is just your standard substitution stuff, just a weird looking nucleophile. Gabriel synthesis, I highly doubt, as neat as that reaction might be, I would be really surprised if that showed up. Hallelujah, wow. Not only were we close, that was the end of it. Okay. Before we completely end it, though, because I know polymer reactions are on there, and we haven't talked about polymers at all, so you might see 1 or 2 questions on polymers. So I want to at least show you something so you get a little idea on what's happening with it. Okay? So ultimately, all polymers are organic molecules that repeat. That's all a polymer is. Okay? So poly for multiple, and I have no idea what mers are, so let's just call them mers. Okay? So at its simplest level, what we're doing is taking a single unit, and then we want to propagate that out into a polymer. So what we're just going to do is repeat it, okay, a whole bunch of different times. And what we'd have there is now a polymer. What if we had different types of polymer or monomers? So in this case, if we had a red and a red circle and a green square, we could alternate them, or we could set them in sections. Do a whole bunch of red circles, a whole bunch of green squares, a whole bunch of red circles, okay, or varying those amounts. So what we end up with in those cases is a different type of polymer because it's being put together in a different type of fashion. Okay? So if we go, both of these are known as copolymers because we have more than one monomer, or more than one type of monomer. If we go in that alternating fashion, we just call it a copolymer. If we go where we've got sections or blocks of those types of monomer units, that's where we get a block copolymer. Okay? So the name kind of makes sense from that. And forgive me, I haven't looked quite a lot at these. You might hear something about cross-linked. Okay? All cross-linked means is that your monomer has more than 2 places to bond. So all monomers at minimum need 2 places. That's how you can extend for longer chains. If we have more than 2 places, we can extend out those 2 directions, but we can now also extend along the other axis, okay? Or depending on the monomer, along any number of axes. What can then happen is if we take a look at this one, our polymers are now linked to each other, which changes the physical properties of the polymer. So where a rubber band we can then stretch and release, we can do that because all of the polymer materials within that rubber band aren't connected to each other. If we go through and now physically bond them to each other, I now can't stretch these 2 fibers away from each other because they're locked at that position. So a cross-linked polymer becomes much more rigid, stiffer, brittle, because it can't do that elongation. It can't do that kind of stretching method. So it's kind of a neat phenomenon. Shorthand, because our polymers can be a whole bunch of different lengths, we want to come up with a different shorthand. Because typically when we look at polymers, we're looking at 500 at a minimum monomer units in it. So to draw out 500 repeating units is a bit tedious. So instead, we go through and we look at our monomers. Sorry, again, I haven't looked at it. And we come up with our shorthand. There are a couple different methods for how you go through and look at shorthand. Everything that I've seen on the ACS test when they ask questions about monomers goes with this method. We put parentheses around our smallest repeating unit. Okay? Sometimes you'll also see a number attached to the lower right-hand corner. That's specifying how many of those monomer units are in that polymer. Relatively simple. When we go through and take a look at our copolymers, we run into an issue here, because that's one way to look at a repeating unit. But couldn't I just as easily have done that? Okay. How we decide the polymer shorthand is ultimately something that was decided by IUPAC. Okay? And as we all know about IUPAC, they're lots of fun-loving people. They decided on a rule, and that's the end of the rule. When we look at our polymer shorthand, the official way to do it is based on electronegativity. So the first atom in your polymer shorthand must be the most electronegative. The next atom needs to be the next most electronegative that's connected to it, okay, in the polymer. The issue with that kind of notation is that very often you lose the structural information. So that maybe the most electronegative atom is on this part of our green block, and the next most is here, which means I would put my parentheses like so, which is a very odd method for going through and designing it, but if it happens, it happens, and that's kind of what the IUPAC system is. Again, like I said, most things that I've seen on the ACS test are grouping polymers according to where those monomers are. So the bond that's forming between the monomers is the bond they drop the parentheses through. Okay? If we look at the block copolymer, that becomes more difficult to deal with. Usually the notation is something along these lines, where they go through and specify your numbers afterwards. We can't get all that specific with it because we can't specify how many were in that section before the next one started. Okay? So you see a slight difference in that. As far as the polymer formation goes, there are 2 types of polymers that you will see. There are the addition polymers and the condensation polymers. Okay? You get different mechanisms for both. Okay? The condensation is consistently a standard mechanism. That mechanism is your addition elimination centered around carbonyls. So if you look at a polymer and you see a carbonyl, you had a condensation polymer, like 90% of the time. Okay? The one exception to that, the carbonyl must be part of the main chain of your polymer. So if we go back to our slides here where we can see these, our carbonyl needs to be in here. It's not something that's hanging off the side of the main chain. Does that kind of make sense? Okay. So if you see that carbonyl, that is a massive red flag for a condensation polymer. Without that carbonyl, we've lost some reactivity. Remember, your carbonyls have that electrophilic carbon, and for that matter, that nucleophilic oxygen. So we get a lot of chemistry around that functionality. To do the addition polymers, you lose the carbonyl. We aren't working with a carbonyl anymore. So we need something else to activate it. Usually, you're looking at a radical mechanism. So your addition polymers are dealing with pi bonds because we need two reactive atoms. Okay, so in the case of our pi bonds, that works really well because each of those carbons is attached to the pi bond. So both of them are reactive and equally reactive. So when we initiate with a radical, both carbons become radically active and can propagate out the chain. The net result, though, if we start with that pi bond and we now turn it into two radicals that can then grow, what happened to the pi bond? Disappears. It's no longer in the structure. Okay? So if you have an addition polymer, your monomer is usually starting with a pi bond, so you're looking for some kind of alkene. The polymer that results from that usually does not have an alkene because the alkene was necessary to react and make the make the polymer. Okay? There are some exceptions to that. If our monomer is long enough that it has more than one alkene, one of those alkenes could potentially stay. It doesn't have to react. Okay? A lot of that is resonance-based. If you take a look at the ACS test book, was it you that I was talking to? There is a question in one of the chapters about polymer formations where it's an addition polymer. Okay? And the alkene stayed in the polymer. And that was because, if you go back to the starting material, there were multiple double bonds. So resonance allowed for a double bond to be maintained in the final polymer product. Okay? So what you're trying to trigger on, addition polymers, you're looking at alkenes reacting. Condensation polymers, carbonyls, and a nucleophile reacting. Okay? So your addition polymers, we've got a general mechanism shown here. I'll kind of pause a little bit and give you a chance to kind of absorb over it, maybe talk through it. Because it is a radical mechanism, we do need that kind of initiation either with light or with heat. You'll notice that what we're starting with is that peroxy functional group. We again have that really weak oxygen-oxygen bond. Light can initiate that to form our radicals. The radical can then react with our alkene in a single electron transfer method. We form a new bond between those two atoms, but we have to account where the other pi electron went, goes to the end of that carbon, which is what we're showing down here. Because we still have a radical, it can now react with another alkene monomer, and we get the reaction continuing, so on and so forth. Okay? Until eventually what happens is we run out of radicals and the reaction ceases. Typically what would happen in the experiment is we'd say the rate at which this occurs, after 5 minutes, all of my chain lengths are on average 500 atoms. Well, I only want 200 atoms, so about 2.5 minutes, I'm going to throw in a bunch more radicals in the hopes to cease the reactions, to stop everything from occurring. Okay? Because once it's now radically dead, then I can extract everything out and I've got my polymer the way I want it to be. The length of the polymer is going to determine a lot of the physical properties as well. Okay? So depending on what you're trying to do, you may get different results. This was the experiment that we did at ASU for our condensation polymers. Notice we've got our carbonyl and our nucleophile. In this case, our electrophile and nucleophile are in the same molecule. So we could, in theory, have these loop back on themselves and just form quick rings. In this case, our chain is so short that we can't form those quick rings. Okay? This should look pretty familiar as well. What we have started with here is effectively an amino acid. Okay? It's a protein. So biologically relevant as far as that goes as well. In the experiment, we looked at this functional group or this polymer earlier. I'm not sure we used this starting material. But remember I talked about nylon 6,6. The 6,6 comes from the number of carbons involved in each of the monomer units. So there's 6 carbons coming from our nucleophile starting material, and there's 6 carbons coming from our electrophilic material. Okay, so sometimes you'll hear the name, a name for that polymer, like a nylon, but instead of it being 6,6, it'll be 4,3, and that's because one of them had 4 carbons, the other monomer had 3 carbons. Shorthand, because I'm afraid this might be the last slide. Not quite yet. With the shorthand, what we're trying to do is again summarize where the monomer or what the monomer was. So for that first compound, what type of polymer do we make? Any guesses? What type of polymer? Addition or condensation? Addition, because no carbonyls. We're looking at an addition reaction. To do our addition reactions, what monomer unit do we need? What functional group? We need radical and we need an alkene, pi bonds. So minimum for an alkene, how many carbons? There's our shorthand for that polymer. Okay? Our shorthand draws the parentheses through the bond, not through the atoms. If we were going to look at the monomer, it's probably something along these lines, CH2, CH2. Okay. If we took a look at this next one, what polymer do we have here? We're looking at a condensation. Again, carbonyl condensation. Shorthand for this, there's a couple approaches to it. Don't have a nice one to show you. One approach would be going through here. Okay, and then if we copied and pasted, so everything within the parentheses, copy and paste either direction, you should see we get the same groups coming across of that. The issue with that is what's the first atom? Carbon, not the most electronegative. So officially, that is a wrong setup to show.
But it makes so much sense.
Yeah, I know. Oh wow, I can't even draw the other one. Officially for this one, I believe where it gets dropped is here. Okay, because we start with our most electronegative followed by our next most, because it's an sp2 versus the sp3. Okay, the issue with that is what's our monomer? Okay, that was our monomer, where the nitrogen could then attack the carbonyl of another one. Our shorthand doesn't show that monomer very well. All those pieces are definitely there, but it's in all a weird shuffled order. Okay? So I don't like the official shorthand because it doesn't make it easy to see where our monomer came from.
But like you said, if we copy and paste it.
If you copy and paste, it still works. Yeah. Almost guaranteed what you're going to see on the ACS exam will be drawn in such a way that you can see what the monomers were that went into it, because they aren't going to go through and show the parentheses cutting through a bond that wasn't made in the process of this reaction. Okay. If you're going to try and identify what your monomer was, so ignoring shorthand, we said it was a condensation polymer, which means we formed a bond between a nucleophile and an electrophile. What's our most nucleophilic atom in this structure? The nitrogen. What's our most electrophilic? The carbonyl carbon. this bond was made. Nitrogen, carbonyl, this bond was made. What's the monomer? There it is. Okay, so it can help you identify where your reaction is. Polymers take a lot of practice to really understand. I don't fully expect you to practice them that much. I just want you to have at least seen it so it's not a complete surprise, and hopefully you can whittle down some of your answer choices. Okay. Yeah, I don't think there's really anything else I can really tell you beyond that. I can point out your other polymer chains. You got one there. This one. If we try to do that rule and put it there, you're missing the carbonyls. That is a bond that was made, though. Okay, it just didn't happen to be the complete thing. So in this case, this one was a block polymer, or a copolymer. We had two monomers. Okay, so it may not always be obvious. On the ACS test, they're probably going to do shorter ones. You won't see as long a carbon chain because it takes up too much space. Okay. I'm pretty sure the next thing, yeah, that's the last slide, and that's not relevant for you guys. So, unless you guys have questions, I am all out. Anything?
I came across one question that talked about an N-butanol. I didn't know where the N came from.
It was a name thing that we just wanted to do with the last.
No, it didn't have a nitrogen in it. It wasn't a capital N, it was a small N.
Oh, I know what you're talking about.
It is a naming thing, but I don't know.
It is a naming thing.
But I don't know what it
Oh,
means.
it's butanol. Al is aldehyde.
Yeah, but you can find N-butanol.
You can find N-butanol, N-butane, N-butene.
What does these N?
I'm pretty sure what the N means,
And if
and
you
don't
don't-
quote me on it. I think it just means normal.
Okay,
There is
that would
no other
explain-
functional group
That
pretty much
would
in the
explain the
structure.
picture of it, because there's nothing special.
So yeah, when you look at the butanol, it's your 4 carbons, whoops, and the aldehyde.
Yeah.
If you look at
exactly.
N-butane, it's 4 carbons.
Okay, so that's.
I don't know the reasoning behind that, why that came up, but yeah, that's what the N
Okay.
means.
Oh, there was this nasty question about if you oxidize these following compounds, are they optically active or not? Is that going to be something you would see in the ACS test? Oh, man. Hey, this is so
Here?
It was on the sapling sample one of the. You have to oxidize it first and then is it optically active?
What does optical activity mean?
Rotation of light?
Okay, it is ultimately a rotation of the plane, well, you're both right, plane polarized light, or polarized. What the heck? Plane polarized, geez, that word is big. Light. Okay. On a written test, I'd say yes, that's a valid answer. You're not taking a written test, you're taking a multiple choice test. So when you hear optical activity, what you should be hearing as far as your test goes is what Zena suggested, which was there's a chiral center. And I would take it almost a step back from that. It's not that there's a chiral center, it's that the molecule is chiral. Okay, and the reason why I say not chiral center is I could have 2 chiral centers and be achiral. And if it's achiral, it's not optically active. So it must be a chiral molecule. Okay. So if it has 1 chiral center, it is a chiral molecule. If it has 2, it could be. It could also be meso. And if it's meso, it's optically inactive. It's an achiral molecule. Okay, so chiral equals optically active, and achiral equals optically inactive. Okay. So really what they're asking you is about chiral atoms. But it's difficult for me to then push beyond that as far as the reaction goes, because if there's two chiral atoms in that, then they're really testing on, do you understand that it could be meso?
Yeah, I'll have to go
Okay.
back and look at that nasty one.
If they only give you one chiral atom, then they're just saying, do you understand that chiral means optically active?
Well, you have to oxidize the molecule they give you first. It's
Yep.
number 80 on the first one, in case you want to look at it.
Through sapling?
Yeah, do the sapling one. Not now.
Oh, I'm not going to be able
all
to
of
do
your
it.
time, but.
My computer's about to die too.
That's
So.
exactly one with numbers. You just have to think about it, but it's something that you've probably never seen. It gives you like the actual value for
Oh, good.
rotation of light or something.
What are they trying to test you on? If you know the numbers
SN1,
already?
SN2, and what should you should know that there's inversion.
Oh, the receiving fish.
Yeah, you just have to know it.
Okay. Okay, that makes sense.
So, yeah, well, what we've got here,
And
or
it's
what's
fine,
written up there, is ultimately just your definitions.
because of the original.
You can see numbers show up in it as well. And this is where you got to be a little bit careful. R and S mean nothing. Okay, so I'm going to write mean nothing, and I'm going to cross that out. You shouldn't be looking at R and S in that respect. What you should be looking at is if they tell you one structure has, say, a +9
That's exactly
degree-
what they tell you. Well, they tell you -9, and it's the
degree
acid.
rotation, they tell you it's 9, and in the course of the reaction you get the opposite conformation, then it becomes -9. So if we're looking at enantiomers, and we say stick with one stereocenter on an enantiomer, okay, one of them will rotate light. Okay, so the arrangement of the atoms forced light to rotate a certain number of degrees to a certain direction.
Okay.
If we change the conformation to the other enantiomer, we have the same arrangement of atoms, but now when light hits it, it goes, whoop, it's all backwards, so it's going to rotate the other direction. But since it's the same arrangement of atoms, it goes the exact same other direction. So if we're just changing the conformation, we go from +9 to -9. Okay? And this is where it can be kind of confused with R and S, because you could look at it and say this one's R, and this one's S. That means the numbers will be opposite. One will be positive, one will be negative every single time, and the number itself will be the same magnitude. Okay? But just because it's positive doesn't mean it's R. Just because it's positive doesn't mean it's S.
I see what you're saying.
Okay? So they are two different approaches to the same idea, that molecules have a handedness to them. In one case, that handedness we put on it absolutely. So we have the structure, and we say this is where the atoms are physically arranged around each other. It is the absolute configuration. And I'm pretty sure that's R and S. The other version is, crap, I have no idea what the structure looks like, but I know when I hit light at it, the light is rotated by this degrees. Okay? And it's either clockwise or counterclockwise, which is where R and S is ultimately coming from. But we set up light to be our complete vertical, and if it rotates off of it, we say, oh, it's positive or negative, depending on which direction it turns in. Okay? So one is based solely on the structure, one is based on how light interacts with it. It would be nice if they were the same. They are not, which is why you must treat them as different independent topics.
That rings a bell. I remember that from something.
But I mean, you're still kind of in that weird gray area, because not only are they completely different, but you must also, there's a lot of parallels. But you have to treat them as parallels. They don't ever cross. Okay?
You're supplying the scratch paper?
Yes. In fact, I will grab that on my way out. I will trade pizza. for secretary's papers somewhere.
You should have to know. Anything else you think we should know?
Good luck. Was it good night and good luck?
That's right. That sounds good.
I don't know about luck. Well, kind of.
Yeah, I don't want you guys to have any luck on it. I want you guys to just know it, do it, and
There's gonna
rock
be
it
some
without
guessing.
any luck.
That's for sure.
Superstars.
I will let you guess on 4 questions. How about that?
Oh, we only get to guess on 4 questions?
Yeah, because if you guess on 4 questions, that still puts you in the 100th percentile. So
Oh my gosh.
Well, how are you gonna know if I guess on more than 4?
you can only miss 4 questions. Is that better?
All right, that's different. What if I'm a really good guesser?